Greetings everyone. In this presentation, we present our paper, a scalable graph learning approach to capacitated vehicle routing problem using capsule networks and attention mechanism. Here we will be presenting the motivation and major contribution, the problem description and formulation, the solution approach, and the learning architecture, followed by the experimental details and results. Here we focus on a capacitated vehicle routing problem, or CVRP. The nature of CVRP is that it is an NP-hard problem. Therefore, the traditional methods such as integer linear programming based or heuristic based methods become intractable for larger size problem. Hence, there is a need for a reinforcement learning based method. But the current state of the art learning based method cannot scale to larger size problem. One way to enable scaling is by learning the local and global structural information, which leads us to the use of graph neural network based learning. Our major contribution involves a new graph reinforcement learning approach for capacitated vehicle routing problem with generalizability and scalability without the need to retrain, which we demonstrates up to a graph size of 2000 nodes. We introduce a new policy network, which is based on capsule network and attention mechanism, which we call CapAM. We compare and contrast the performance gain of our method compared to a set of baseline methods. And finally, we extend our method to include demand uncertainty. In the capacitated vehicle routing problem we consider here, it consists of a single vehicle which has multiple routes. There are n locations with a depot. The vehicle has a maximum capacity. The locations has a demand. We do not consider a split delivery. The objective of the mission is to minimize a cost. Here the cost is the maximum distance traveled by the vehicle in order to complete the mission, abiding to the capacity constraints. In order to apply a reinforcement learning based solution to the CVRP, we formulated it as a Markov decision process, or MDP, that enables a sequential decision making. The state space consists of the current location and the capacity. The action space is all the available task. The task which is chosen during a decision making will be visited next. And the reward here is a delayed reward, which is the negative of the total distance traveled. The CapAM policy network consists of an encoder, a decoder, and a context. The encoder is based on capsule networks, which captures all the node properties and also its neighborhood information and generates permutation in various node embeddings. The context represents the current state, which gets updated every time a decision is taken. And there is an attention-based decoder, which is based on multi-head attention mechanism, and it generates output probabilities using node embeddings and the context for all the available nodes. Looking deeper into the encoder, the main function of the encoder is to represent the properties of the nodes along with the structural information as a continuous feature vector. Initially, the tasks are represented as a graph, and the encoding is based on a capsule network on graphs. It generates a permutation in various node embeddings, which captures all the node properties as well as the local and global structural information. The context represents the current state of the vehicle when a decision is being taken. It gets updated every time a decision is taken. The information encoded in the context consists of the location of the vehicle and the current capacity of the vehicle. The main function of the decoder is to use the information from the encoder and the context to generate output probabilities for all the nodes available during a decision-making instance. The decoder is based on a multi-head attention mechanism. Here the main idea is to compute which node is the most important given the current state. The importance is represented as output probabilities. Here we assume a greedy approach, which means the node with the highest probability is being chosen as the next destination during a decision-making instance. Here we present the sequential decision-making process using the CAP-AM-RL model. Initially, the tasks, which is represented as a graph, are being fed to the encoder, which also consists of the structural information related to the tasks, and it produces permutation invariant node embeddings. The state of the vehicle is being fed to the context, and the information from the encoder and the context is being used by the decoder to generate output probabilities during a decision-making instance. The whole CAP-AM model is being trained using a policy gradient method. The simulation environment is programmed using Python 3.7 using the PyTorch library. For the training, we considered the graph size to be 100. The algorithm used for training is the reinforce algorithm with a rollout baseline with a number of epoch as 100 and the number of sample size per epoch as 500,000. The optimizer used is Adam with a step size of 0.001. The training has been implemented using 2 GPUs. In order to test the trained model, we tested the trained CAP-AM model on graph size varying from 50 to 2000. We compared with 4 baseline methods, where the first one being a guided local search and simulated annealing, an attention-based reinforcement learning method, and a graph convolutional network-based reinforcement learning method. The first 2 baseline methods are non-learning based methods, and the last 2 methods are learning based methods. The trained CAP-AM model is tested for generalizability and scalability. In order to test for generalizability, the performance is compared for graph sizes less than 100 nodes. For each graph size, we considered 100 different scenarios, and the performance is compared based on the average cost function across this 100 scenarios. As we can see, the CAP-AM model was able to perform better compared to the non-learning based methods and on par with the learning based methods, which is the attention based RL method and the GCN based RL method. In order to test for scalability, the performance is compared for graph sizes which has more than 100 nodes. For each graph size, we consider 100 different scenarios, and the performance is compared based on the average cost function across this 100 scenarios. As we can see, the CAP-AM RL method performs significantly better compared to all the baseline methods, with a significantly faster computation time compared to both the non-learning based methods, as you can see from the table to the right. Based on this, we can say that the CAP-AM RL demonstrates the advantage of better structural encoding compared to the AM RL method and the GCN RL method. Apart from generalizability and scalability, we also extended our method to include demand uncertainty. Here, during each decision-making step, the location demand varies following a Gaussian distribution. The main formulation update here is on the node properties, where the node properties includes the demand uncertainty parameters, which include the mean demand of the node and its standard deviation. Here we compared the performance with the CAP-AM RL, which is trained without considering the demand uncertainty. As you can see from this figure, the CAP-AM model, which is trained without demand uncertainty, performs poor compared to the CAP-AM model, which is trained considering the demand uncertainty. On summing up the work done in this paper, we introduce a graph reinforcement learning method using capsule networks and attention mechanism as policy for a capacitated vehicle routing problem. We demonstrate better generalizability and scalability compared to the state-of-the-art baseline methods. We also extended our method to incorporate demand uncertainty. As future direction, we will be extending to scenarios with dynamically generated locations. We will be exploring other policy gradient methods such as proximal policy optimization, and also explore non-greedy based decision making. This work is supported by the National Science Foundation and the Office of Naval Research. Thank you.